So hi, welcome to the Rock Museum. I'm here with Dr. Schultz, Dr. Schultz, would you just like to introduce yourself to everybody?
Sure. Thank you for having me, Andrew. My name is Dr. Rich Schultz, and I am a geologist. I've worked as a college professor for many years, teaching geology and earth sciences.
Brilliant. So I couldn't ask for a better person to actually come and have a look at our rock museum. Today we're looking at metamorphic rock, and listen, if you would be able to give the students a little introduction to metamorphic rock, that would be absolutely amazing.
Sure. We're looking on the wall at something called the rock cycle. The rock cycle is never ending. It goes on all the time and has been since the beginning of the Earth, if you will. What you're seeing spinning to the side there is a rock called marble. A metamorphic rock actually didn't start out as a metamorphic rock. It started out as in this case, a sedimentary rock. The sedimentary rock that marble comes from is called limestone. And many of you have probably heard of limestone. It's used many times for building stones and so forth. Limestone forms under sedimentation. So you can see sedimentation on the rock cycle there. It is buried. It undergoes heat and pressure. So as it undergoes heat and pressure, then it begins to change. The amount of heat, the amount of pressure, the more that it goes through means the more that it's going to change. The marble that you see that's spinning, that is a textured rock that is called non-foliated, meaning that the minerals that are in it do not line up. They're sort of in a random arrangement. The minerals that are in there are predominantly a mineral called calcite. Calcite is a rather soft mineral. It forms in crystalline shapes. Many of the limestones that you see are almost entirely calcite. And that rocks that we see every day are really practical in terms of their uses.
Thank you. What's the difference then if we move across from metamorphic rock to igneous rock, which I'm just moving across to now?
Yeah, let me follow you here. Let's take a look at the igneous rocks. Now, igneous rocks form in a little bit different type of setting. They're not formed under the heat and the pressure so much as they are formed within magma deep below the surface of the Earth. So magma is really molten rock that is below the surface. Molten rock that makes it to the surface and comes out of a volcano is what we call lava. So magma, lava is the same thing except of where it's located. Magma is below the surface and lava is above the surface. The igneous rocks that you're seeing here form under different sorts of settings, what we call environments. The one that is right in front of me right here, it's a pink one, is a rock called granite. Granite is pink because of a mineral that it contains called orthoclase feldspar, or sometimes called potassium feldspar. And that's what gives it the pinkish color, is that mineral potassium feldspar. All rocks are really a collection of minerals. Mineral is our basic building block of rocks. So the pink one there is orthoclase feldspar. Now you look at the rock that's just to the side of that, that's black and white, right, yep, the one that's that's it, yes. That one doesn't have the pink mineral in it. So we know it can't be a granite because a granite is defined as having a certain amount of the potassium feldspar in it. And so this rock would be classified not as a granite because it doesn't contain the potassium in it, but it would be classified as a rock we call diorite.
So these are all igneous rocks. Why is this one shiny?
Okay, that's obsidian. And you notice the rounded fracture there? That's called a conchoidal fracture. So it fractures much the way glass does. So there are two different environments for igneous rocks. One of those is below the surface. We call those intrusive igneous rocks. And the one there right in front of us, the obsidian, that is an extrusive volcanic rock, which means that it's come out of a volcano and it crystallized, it cooled, it solidified so quickly that none of the minerals had time to grow and develop. It just cooled almost instantly. That's why we don't see all the crystals in the obsidian. And in the granite, it grew rather slowly over time, and it cooled under conditions that it took a long time to cool. The longer it takes to cool and solidify, the more the crystals have a chance to grow and get larger.
So that's amazing. You know where I'm taking you next, don't you? Which across to sedimentary, if that's okay with you.
Sure. Sedimentary rock is the only rock of the three types, igneous, metamorphic, and sedimentary, that forms exclusively on the surface of the earth. So when we say sedimentary, or sometimes we pronounce it sedimentary, it has the word sediment in it. And what is sediment? Well, sediment is particles of rocks and or fragments, perhaps, of organics material, of minerals, of rocks, and they are solidified or consolidated and cemented together through time. One layer forms sort of like a layer of sand, then there's another layer over the top of that, then there's another layer over the top of that, and as these layers are added on, the weight from the overlying crystals and minerals and so forth, they crunch that down and they help the lower rock to solidify. And the word that we use that rocks are cemented together, the minerals are cemented together into a rock, is called lithification. Lith, L-I-T-H, is the Greek word for rock.
And we were looking at sandstone, Dr. Schultz. Can you just talk us a little bit through, because obviously the significance of Uluru for Australians, Indigenous, and for everybody here in Australia is such a huge megalith. Can you just talk us through about some of the sandstone and how it's formed and how Uluru would have been formed in the past?
Absolutely. The sandstone, which comes in many different varieties, is essentially quartz minerals. That's predominantly what sandstone is made out of. And they are glued together, if you will, by silica. But sandstone is formed in layers as a sedimentary rock, one on top of each other, very much like putting down pieces of paper, one on top of each other until they get stacked up. And that's what you see here in this photograph on the wall, are the various layers. We call those beds. So it probably takes on the order of thousands to millions of years to form each one of those layers, those beds.
So can I ask you a question? Sorry to interrupt you. This layer across here it seems to be a different angle. Can you explain that, please?
It is indeed, yes, and that's a great observation because that's called an unconformity. We actually, there are three different types of unconformities, but the one we're seeing here is called an angular unconformity. And you can see that the rocks below that line are at an angle, and then there's the horizontal, and then the rocks above it are more parallel to the earth, the surface. So what we're seeing here is rocks that were formed in layers on the bottom where the people are walking there. Then a geologic event happened to tilt these rocks, perhaps tectonic forces, and then sedimentation picked up again and formed layers above those tilted layers that are below it. Another interesting thing you can see also where that line is, and Andrew, if you can use the pointer where that line is one more time. Above that, in the rock in the middle, right there, right where you have your pointer, those are called cross beds. So imagine a situation where you're in a river and the river is carrying sand as part of its bed load, is what we call it, and it's churning around in the water depending on the speed of the river. The higher the velocity of the water, the larger the fragments that it's going to be able to carry. And what it's told us here is that cross-bedding is taking place, so there are literally layers that are forming on the sides of that riverbed at an angle.
That's amazing. So if we look at Uluru, as I think you mentioned it as a sandstone megalith, how does the picture on the right relate to Uluru as a sandstone rock? So I'm here today with Dr. Schultz, and we're at Uluru, and the traditional owners of the land are the Anangu people, and we're going to be very respectful of that as we move around. But Dr. Schultz, would you be able to sort of come with me as we fly around, and being careful not to actually walk on the rock, which is
What you're looking at here is Uluru, but Uluru is significant because it's of religious significance to the Aboriginals from this area. It is made out of sandstone, and the orange color that you see is an indication that there's a high percentage of iron that's present. We refer to that as ferruginous, from the Latin Fe, chemical symbol for iron. So Uluru here is literally a monolith, a large chunk of sandstone that was once horizontally layered parallel to the surface of the earth. Now you see the lines that we're looking at on the top, those look to be perpendicular to the surface of the earth. Now, one time they were not, they were parallel. So that's the same way with layers of rock. We know that the oldest is on the bottom, the youngest is on the top. So Uluru fits into this because it is a large monolith. It's about 5 kilometers or so if you were to walk all the way around it. And it is literally just the tip of the iceberg here, because there is a great deal of rock that is below the surface of the earth, but only the tip is showing here. And all the rock around the area of Uluru has been eroded away. So that tells us also that this type of sandstone is rather resistant to weathering and to the superficial processes. Otherwise, it would have been weathered away also.
So is it, sorry to interrupt you, is it true then that when this was first formed, it would have been underwater?
Probably. Sandstone forming underwater is usually the way that we see it happen. It could form in drier areas also, just like a beach. You know, you see the layers of sand that form along the side of a beach. And through time, you'll see layer upon layer upon layer that's brought in by the wave action. And it's deposited one on top of each other. And the sheer weight of all of the rock pushes down on the bottom and compacts that rock so that it eventually gets solidified.
Is it so? A question that one of the students asked was, how is it that you don't get many fossils in sandstone?
Well, one of the reasons is because the fossils that form are marine fossils. And the sheer energy of what's happening when sandstone is formed, those just don't stand up to it. The fossils are rather soft. They're calcareous material. They tend to erode away very easily. And we see those traditionally in a marine environment, with some exceptions.
Okay. Can I ask another question? When rocks are formed, is it possible for rocks to change from one type to another?
Absolutely. So, for example, a sandstone here, if it were to be buried and underwent a great deal of heat and or pressure below the surface of the earth, it's going to change. And the word that we use for that change is called metamorphism. Meta means change, morph means structure or form. So literally changing structure, changing form. So a metamorphic rock that would be produced from sandstone is called quartzite. And that makes sense because most sandstone is composed chiefly of the mineral quartz. So we would take sandstone, put it under heat and pressure, we metamorphose it, goes under that change, and it becomes quartzite.
That's amazing. Listen, Dr. Schultz, thank you so much for coming to the Rock Museum and then also to flying around Uluru with us. And hopefully this is the beginning of many talks that you might do for our students. And so, thank you so much for coming.
No, thank you for having me. I'd love to do it.